From San Francisco, I'm Moira Gunn, and this is Tech Nation. Today on Tech Nation, it's Nobel Prizes Explained 2013. My guests today are all professors from the University of San Francisco. They are panel chair and finance and economics professor Ludwig Chincarini, English professor Dean Rader, politics professor Stephen Zunas, astronomy and physics professor Aparna Venkatesan, economics professor Jesse Antilla Hughes, and biology adjunct professor and UCSF postdoc Jason Fernandez. Ludwig, Professor Chincarini, as panel chair, let me start with you. You emailed me about your Nobel Prizes Explained panel, and I emailed you right back. What a good idea. Tell us, how did you come to this idea?
Well, the Nobel panel is getting together a lot of professors that are experts in their field and explaining to a general audience what the Nobel Prize was awarded for and the details of it. So, the common public can understand the important contributions that were made in different fields. And the way it came about is several years back, I had a friend who used to call me and ask me, who's going to win the economics Nobel Prize? So I would try to guess it. And then I would write an ex post description of why they won it. And I started sending it to people. Then I started sending it to some Nobel Prize winners. Then I started sending it to a bigger and bigger list. And it sort of became a thing. And in fact, now I get asked to talk on the newspapers or other places about it. And so then last year, it came to me that it would be nice to have this for the other fields, which I know nothing of. And so last year was the first time that I asked some USF professors, would they like to do this? And we did it, and it was great. A lot of people learned. I learned a tremendous amount. And so we've continued it this year, really.
Well, let's start simple. Let's start with the Peace Prize. And we have politics professor Stephen Zunas. Welcome, Stephen.
Good to be on.
Now tell us, what's the prize? What does it mean? What does it mean in the who got it, and what does it mean in the spectrum of why is this so important?
Well, the Peace Prize is one of the most closely watched of the prizes, in large part because of its political implications. Unlike the other prizes that are awarded in Stockholm, this is awarded in Oslo, Norway. And the choices have varied from activists who've worked for human rights and social justice to political leaders who have, many of whom had been warring against each other, who finally made peace. Thus, some of the more ironic awards like Henry Kissinger, Yasser Arafat, Menachem Begin. But there's also been a trend, particularly recently, of giving the award to international organizations, as we've seen this year with the awarding the Nobel Peace Prize to the Organization for the Prohibition of Chemical Weapons.
Now, what does that organization do?
Well, it was established to enforce the Chemical Weapons Treaty, which was originally drafted in 1993 and went into effect in 1997. And they're charged with the recruiting countries to sign on to it, which they've been quite successful at. 189 countries are now parties to the treaty. Only 6 have not yet joined, and as well as overseeing the destruction of these weapons. Now, the use of chemical weapons was originally banned in the 1925 Geneva Protocol, which came after the horrors of World War I. And despite a number of glaring violations of that, particularly Iraq against Iranian troops and Kurdish civilians during the 1980s, it's largely held. Even throughout all the horror of World War II, this ban was observed. But there is also a realization that the world will never be safe until they were completely eliminated. And this is the charge of the OPCW. And they've been quite successful so far under their leadership. 80% of the world's chemical weapons stockpiles have been eliminated. And they're on course to eliminate most of the rest of them.
Now, let me ask you this. This is a non-governmental agency, an NGO. Or as we would say.
Or actually, technically speaking, it's an IGO, an intergovernmental organization.
Oh, okay. So it's an intergovernmental agency. Mm-hmm. And that's the next question is, where does the money come from? Mm-hmm. So all the member states, I imagine? Yes,
and they have a fairly small staff. It's and a fairly small budget. I think it's less than $500 million, and they operate out of The Hague. And they include some of the leading technical experts in the field. They are they have. They've had a lot of their work cut out for them, given the enormous stockpiles. In fact, United States and Russia, which have the largest stockpiles, are actually behind in the elimination. We were supposed to get rid of ours, and then the Russians as well by 2007. We were given an extension to 2012. At this point, it looks like it could be at least 2020 before they're all done. This is not because I think of any efforts at cheating or deliberate foot dragging, but it's largely technical. But it is quite a process, given the technical issues involved. But they
can't just dump them down the drain, right?
Yeah, exactly. But,
it just occurred to me. Yeah.
But they are doing remarkably good work. Indeed, in awarding the prize, the Nobel Committee stressed it was not just the recent issues around Syria for which they won the award, but in fact, it was primarily for the important work they'd already done.
So what do they do in Syria?
Mm-hmm. Well, in Syria, in many ways, it's similar to what they've done in other countries. The difference, of course, is that they're doing it in the middle of war, and which is, of course, more challenging. But despite some skepticism, at least the initial reports, these first few weeks, they've been remarkably successful at identifying and starting to collect the chemical weapons. The Syrian regime has been surprisingly cooperative so far. Right now, they're trying to figure out how much they should do inside Syria, or whether they should try to remove the weapons physically to another country and then dismantle them there.
Well, I'll tell you, let's go into a war zone and ask them to give us their weapons. I don't know. This doesn't sound like a really great... I'd give them a prize, honestly.
I mean, what's interesting about it, though, and I think one reason they did get the prize, in addition to, of course, their good work up until now, is that, when President Obama announced the intention of taking military action in reaction to the horrific chemical weapons attack from back in August, there was an alternative. There was a diplomatic alternative. There was not an OPCW. They would not have had this option. And so I think in many ways it underscored the Nobel Committee's recognition that having disarmament done on a universal basis, this idea of universality, that all countries should be parties to a treaty. And in certain ways, I think it was one could even interpret it as a slight rebuke to those in the U.S. and Britain and others who've insisted that arms control can be done through unilateral military action, and recognizing that this principle of universality is really the only thing that has worked historically in ridding the world of dangerous weapons and of reducing the risk of conflict using unconventional weaponry with all the horror that comes with it.
So it's really peace prize. It's peace, not war.
Very much so.
So very much so. That's great. Well, let's move on here to the Nobel Prize for Literature. English professor Dean Rader is with us, and tell us what was the prize awarded for this year.
The prize this year was both surprising and not surprising in terms of who it went to. It went to the highly regarded Canadian writer Alice Munro, who has spent her entire life crafting short stories. She's the only Nobel Literature laureate who writes fiction that I can think of who's never actually published a novel. So she's written close to 20 collections of short stories, almost all of which are set in her native Ontario. And her poems, rather her stories, tend to focus on the interior lives of mostly women, but also women and men, as they kind of navigate the nuances of small-town life in Canada.
What's the Literature Prize about? I mean, we can understand the Peace Prize is seeking to create peace in the world. What is the Literature Prize about?
It's a great question. I've always found the Nobel Literature Prize an unusual animal. You have all these other prizes like physics, or physiology, medicine, peace that seem to obviously benefit humanity. And the Literature Prize is the only one in the arts or humanities that has this more subjective component to it. It was one of the 5 original prizes outlined in Alfred Nobel's will. And he originally wanted the prize to be awarded to a writer whose work in the field of literature was the most outstanding in what he called an ideal direction. And early on, that notion of idealism was taken very seriously by the committee. And so writers whose work was grittier or more realistic, like Tolstoy or James Joyce or Proust or Henrik Ibsen, didn't win the prize. And it tended to go to writers who maybe sort of looked to literature as this way of articulating an ideal. And more recently, the notion of ideal has been translated as an ideal notion of humanity. So human rights and issues of oppression have worked their way into the awarding of this prize, which made Alice Munro's selection particularly compelling because she has stayed out of politics in every possible way. She is not herself particularly active in politics. Her writing never veers into the arenas of race or class. She stays in this small town and crafts and hones and crafts and hones these unbelievably intimate short stories. And the fact that the committee saw this work as deserving of the prize is, I think, encouraging for a lot of writers.
Actually, I wonder if everybody in the committee voted for somebody else and she was the only one left. I mean, is that possible? Could that be?
It seems possible.
What's not to like about her?
Well, there's some speculation that she was in the running in the past, but she announced earlier this year that she was going to retire from writing. She's been sick. In fact, she's not going to be able to attend the ceremony this year. So some people wondered if this award this year was acknowledging and honoring her longtime commitment to the field and to her craft.
Because it cannot be awarded posthumously.
It cannot.
So all these awards must be living people as of this date. You're listening to Tech Nation. I'm Moira Gunn, and you're listening to our Nobel Prizes Explained 2013. My guests today are all professors from the University of San Francisco. They are finance and economics professor Ludwig Chincarini, English professor Dean Rayner, politics professor Stephen Zunis, astronomy and physics professor Aparna Venkatesan, economics professor Jesse Antilius, and biology adjunct professor and UCSF postdoc Jason Fernandez. Well, okay, so we got the Peace Prize in the literature. If any, but you got to be able to understand those two. Now we're getting into a little trickier pathways here when you start to get into the science area. So let's start. Everyone has goes to the doctor. Everybody needs medicine. Let's go to the prize in medicine. Jason, tell us about this prize.
Yeah. So thanks, Moira. So I think when we talk about the Nobel Prize in Medicine, we have to start with the fact that there's no Nobel Prize in biology. So typically what happens is the medicine prize will go to a biologist, or in some years the chemistry prize will actually go to a biologist, if there's in fact a medical...
Interloping in there. It's science, so
yeah.
It finds its way in there sometimes.
Yeah, I mean, I think that had to do with when Alfred Nobel said his will, biology was really not what we think of biology today. It was not, a lot of the molecular mechanisms were not figured out, and it was a much more young science. And so I don't think it really fell in his sort of view of what should be awarded. But these days, obviously, a lot of applied chemistry and a lot of medicine starts with molecular biology. So this year, the prize went to three scientists. It went to James Rothman at Yale, Randy Schekman over across the Bay of Berkeley, and then Tom Sudoff down the peninsula at Stanford. And the Nobel Committee, their official designation was for their discoveries of machinery regulating vesicle traffic, a major transport system in our cell. So that...
Well, yeah, see, that's why we have this show.
Okay,
this
yeah, exactly.
People
so
just don't get that.
That sounds like a little much for probably the average listener. But I think the important word in there is traffic, okay? So these guys really figure out the traffic system of a cell. So I like to think about what's sort of the fundamental question you're answering. So here, what they're trying to think about is, if we think about a cell, we can really think of it as sort of like a bag of water, and sort of higher order organisms like people, their cells actually have little compartments in them. And so one of the fundamental questions is, how is information going to move from one compartment to another? And then how is information going to move from one cell to another, right?
What's moving? What kind of information is moving?
So it can be all kinds of information. I think the easiest to probably understand is to think about like a neurotransmitter. So if the sensation from being hit in the knee is going to be processed in your brain, that signal somehow has to be carried throughout your body.
It has to go all the way up from your knee to your brain.
Yeah, it does. And so there's going to be a particular point in the system where cargo that's going to be triggering all those sorts of reactions has to be carried from one spot to another and then has to be unloaded. So the same way like a drug may trigger a certain action, you have sort of natural small molecules within you that can trigger certain actions.
So I have all these cells and molecules in my body, and they have to communicate.
Yeah. An analogy I like to make is if we think about like the mass transit system of San Francisco, right?
Which is on strike.
So there's
Go ahead, Jason.
There's actually a.
It's over. I thought it was over.
Is it over?
Yeah, it's over.
Well, I'm the last to know. Yeah.
But there's actually I think a good analogy with that. So, one of the things Dr. Sheckman did, his portion of the Nobel was for figuring out what genes are involved in this sort of traffic pathway system. So it would be like Bart going on. So he would take a yeast cell and he would knock out a gene. And then he would say, if I basically disrupt that gene.
Are you still talking to me? Yeah. Is that the kind of thing?
Does the traffic system work? So it'd be like if Bart goes on strike, obviously the traffic system changes, right? And so those were the experiments he would do, and he would come up with a list. And he would say, well, these are the genes that are involved in the traffic system inside the cell. And then Dr. Rothman he was addressing the same sort of question, but he tried to sort of build his own traffic system. And then Thomas Sudoff, his contribution was to then say, well, if this whole traffic system, okay, now we've sort of established the parts of the traffic system, how do the doors on your train in the traffic system, how do they know when to open and close, right? And so he discovered that actually calcium is one of the main triggers for the doors opening on your cargo system and letting that cargo out, so letting neurotransmitters out. And so that's kind of mind-boggling to think every once in a while, is that the movement of calcium ions in a cell is going to actually be very well connected to how you form your thoughts, how I'm actually able to speak into this mic right now. That's in some way in part due to calcium ions just moving around, right?
As well as the donors to KQED and National Public Radio everywhere. But calcium ions were involved in the commitment of this program. And so, I think I'm getting it here. It's like it took these three scientists and, of course, people that they worked with. Everyone stands on the shoulders of giants in science to take different portions of this very specific science area together to say, hey, here's how these things work. Not any one really does it. You got to put them together.
Yeah, I think so. Dr. Sheckman and Dr. Rothman definitely worked together. They were very conscious of each other's work. And Dr. Sudoff came in a little later, but he actually made a little remark when he was awarded that he was actually very glad that the Nobel Committee put them together in the same award. He didn't actually work with either of the other two professors. He worked quite closely with another professor, Dr. Scheller, who's currently at Genentech, and who unfortunately was a casualty of the rule of three, that only three scientists can win the Nobel. But you can see there were many, many scientists involved in these really sort of foundational discoveries.
Well, we will be talking about some of the just the casualties of Nobels and some of the process here later on. But let's go down further. Now, Aparna, I'm going to ask you to talk about physics. Tell us about the Physics Prize.
Sure. Thank you, Moira, and thanks for having me today. So the 2013 Nobel Prize in Physics was awarded to two physicists, Francois Englert of Belgium and Peter Higgs of the United Kingdom. These two gentlemen are in their 80s, and Professor Higgs is at the University of Edinburgh, emeritus, and Englert is also professor emeritus in Belgium. They were awarded this prize, the Nobel Prize in Physics this year, for coming up with the theory of the Higgs boson particle now almost 50 years ago. They came up with it independently in 1964. And in fact, they did not meet in person until the announcement by CERN's Large Hadron Collider last year, 2012. They did not meet in person until that announcement, and they showed up to offer explanations and so on. So that's a very interesting story there.
Well, that's great. Now, what does that mean in the total scheme of physics? I mean, because a whole lot of people don't know anything about physics mainly, and it's like they're going out giving these awards. Like, what does this mean?
Yes, I certainly. The Higgs.
Apologies to the entire physics department there.
Not at all. Not at all. I was just reflecting that the Higgs boson is one of the few, I suppose, fortunate particles that has a somewhat sexy popular name circulating, the God particle, actually coined by physics Nobel laureate Leon Lederman in a book that he wrote in the early 90s. It has since met with a lot of
branding and PR. What can I
branding
tell you?
As well as resistance. So let me start out by explaining what a boson is, and then talk about what the Higgs
boson is. We'll see how that goes.
Yeah. Then we can reassess and move forward. A boson is an integer spin particle, meaning, 0, 1, whole values, whole numbers, particle that essentially mediates between forces or other particles in the universe. Now, some of the matter in our universe is made up of the counterpart to bosons, fermions, named after Enrico Fermi.
I'm with you. Yeah, I got him. Yeah.
Bosons named after the Indian physicist Bose. But fermions are half-spin particles, and typical examples are the quarks that make up the normal matter, and so on. Okay.
You're listening to Tech Nation and our program on Nobel Prizes Explained 2013. We'll talk more after a break. Coming up in the second half of our show on Nobel Prizes Explained 2013, more prizes for everyone and Nobel Prizes rethought for the modern age. Stay with us. You're listening to Tech Nation and our program on Nobel Prizes Explained 2013. I'm Moira Gunn. My guests today are professors from the University of San Francisco. They are panel chair and finance and economics professor Ludwig Chincarini, English professor Dean Rader, politics professor Stephen Zunis, astronomy and physics professor Aparna Venkatesan, economics professor Jesse Antilla Hughes, and biology adjunct professor and UCSF postdoc Jason Fernandez.
The Higgs boson is essentially a particle that's an expression of a wider background energy field, the Higgs energy field, that is thought to have pervaded the universe really from early times. However, after particular transitions in the very early universe, and now I'm really talking the first tiny fractions of the billionth of the first second of the universe's life, acquire mass in the presence of this Higgs boson field. So when the four fundamental forces of our universe were around at the beginning, they were all unified, we believe, in one single force. But as the universe went through a series of transitions, again, in the first tiny fractions of a second, as these forces separated out into the four forces we know today.
Which are
gravity, the electromagnetic force, the weak nuclear force, and the strong nuclear force. As they separated out, the Higgs field allowed, through these transitions, some particles to acquire mass while others remain massless. Now, the current best model at explaining why we have the zoo of particles we do, the forces we do, is called the Standard Model of Physics. And it explains the many families of light and heavy particles and so on. Slowly but steadily, many experiments had been finding many of these particles, the tau neutrino, the electron neutrino. It had been building up. One of the few remaining discoveries was the Higgs boson, because it was one of those cornerstone pieces that let us understand why we have the universe we have and why some things have mass but not others. So the Higgs boson, which is a mediator particle, expression of this Higgs field, has a mass of about 127 GeV per c squared, which is a poor man's gram, a unit in particle physics, about 127 times the mass of the proton. Other bosons don't. For example, the photon, which mediates the electromagnetic field.
This is really important because it enables the creation of mass, and with that mass, they ain't no me and they ain't no you, right?
Yes. The mechanism that enables this creation of mass is this Higgs energy field, of which the Higgs boson is an expression. But without that, it's not clear how particles would have acquired mass. And I want to be clear that this Higgs boson is the 1% that enables the 99%, in this case, enable. It's thought to be important not just for matter like you and me, baryons, the normal matter, but also very, very important for theories of dark matter, which is a whole other topic. But the presence of this particle is also because dark matter doesn't interact through the emission of radiation, but it sees the Higgs boson through gravity, and it is thought to be a very fundamental connection as well. So we're still early in this game. Having found this, now we need to make the connection and sort of see what new surprises connecting these now to these other unsolved problems in astrophysics brings. And I wanted to also say I think this is wonderful in a broad human sense of how do we have mass? How did the universe originate? Even the fate of the universe might be tied to this discovery. But it's also a great argument for just, big experiments, for the big questions.
You need the big ones to explain it in this case.
Yeah.
And without that, you're fumbling in the dark. I did have to take my share of physics and being in engineering, but I confess I got through it on math. If I could do the math, I could answer the questions. Understood next to no physics. But that said, if you have something like a Higgs boson or you have anything that you can't grasp, you have sort of this kludge factor, like what's going on, but the math can't address it until you understand the physical phenomenon. And sometimes it goes in either direction. The math is telling us there's something out there, start looking. But in many cases, you've got to be able to find it so that all the math works out. And sometimes then you go back to the math and it says, there's still something missing. It's like balancing your checkbook. Where did it go?
Yes, exactly. I think that this was predicted almost 50 years ago and that all these other particles in the Standard Model were slowly discovered, but this remained. I think it's a wonderful triumph. Now, I think we're still hoping for some surprises. People had hoped when they smashed these beams together, they would kind of find
little signs,
perhaps new supersymmetric particles, some surprises. But this has been anticipated and now found, which is great. But we're still hoping for some surprises. It's very elusive. Its lifetime is only 10 to the minus 25 seconds. And although Englert was available by phone, Higgs himself proved as elusive as the particle because he went on this extended walkabout and was unreachable for days.
Time went by just like that.
Yeah. Yeah, when the Nobel Committee was trying to reach him.
Ludwig.
Aparna, can I ask something? How can they know? What always amazes me is how you mentioned that this happened in the first few seconds of the universe. How can they know that?
I know it sounds implausible, even overreaching, but we do. It's amazing. So how do we know that? Well, there's just a number of ways that we can't physically see back with our telescopes to that time. That's a whole other side topic. The farthest we can see back is when the photons, which we now know as the cosmic microwave background, the largest radiant body of energy in the universe, when that was last in contact with normal matter, such as you and me. And that's a cosmic age of about 380,000 years. So that's the farthest we can physically look back to our telescopes. Beyond that, we're relying on our models of physics and the predictions they make and looking to see if we can assess, what went on in the first few minutes, as well as the first tiny fractions of a second. So the physics of the first few minutes, we have been able to test through, for example, the element of light, the lightest elements, hydrogen, helium, deuterium, lithium. These element abundances in regions of the universe that haven't been polluted by stars too much. They have confirmed for us the physics of the first few minutes. Like, why did the universe get only so far and not farther with element synthesis? Going back even farther, and I would say the current limit to how far we can, test our current models of physics is 10 to the minus 43 seconds, I believe is the number. That is when the entire universe was packed well within the scales of an atom. And related to that, the reason the Higgs field is important is because when the four forces started to separate from each other, the universe went through an incredible period of expansion, we believe, called cosmological inflation, where it just expanded tremendously in a very short period of time, much faster than it is expanding today. And it's almost like we need such a Higgs-like particle and a Higgs-like field to have existed back then, and we needed something like inflation to have happened in those first trillions of a second to explain the universe we see today, because the universe is so homogeneous in every direction you look, and the universe has all these other properties, and we also needed an explanation for what were the seeds of galaxies today, and we can only understand that if quantum fluctuations at 10 to the minus 43 seconds were suddenly stretched out. The universe expanded by a scale factor of 10 followed by 30 zeros very quickly. We can only explain the current universe we have today if we have something like that happen. And so it's sort of working backwards from what we see today and what needed to have happened in the initial conditions.
Wow.
Now let's look at economics. Jesse, tell us about the economics prize.
Sure. One of the first things that's kind of important to say about the Nobel Prize in Economics is that it wasn't actually declared by Alfred Nobel in his will. So the Nobel Prize in Economics is the only new addition to the prizes, and it first started in 1968. It's actually funded separately as well, but it follows more or less the same kind of procedure. And over time now, it's announced basically at the same time as everything else. So this year's Nobel Prize was particularly interesting because, for one thing, sometimes in economics you get these Nobel Prizes that are a little bit difficult to explain to a general audience. But I think in this case we actually had one that was pretty reasonable in the sense that it was a prize in asset pricing. So specifically
asset pricing.
Exactly. So the analysis of asset prices, which sounds technical, but really it was just trying to figure out how stocks and bonds and financial markets work. Right. So this is very foundational research, going back pretty far. And the award was to three guys, Eugene Fama, Lars Peter Hansen, and Robert Schiller. And each of them sort of played a very different and interesting role in this, specific prize. So Eugene Fama is probably within it's all these guys are famous guys. But Eugene Fama is best known for the efficient markets hypothesis. And what the efficient markets hypothesis says, there's a couple of different technical ways of thinking about it, but sort of the most general form of it is that you can't really make money in a financial market with public information.
You've got to have insider stuff.
Right, exactly. So more generally speaking, you can think about this as, everybody out there is trying to make a buck in the stock market at any given time.
That's why they're in it.
Exactly. And they're trying to use all of the information they can get at any given time. So in general, any bit of public information that you could possibly use to try and predict the market is generally not going to really help you out that well. What's interesting about that specific bit of insight is that it actually dates all the way back to Eugene Fama's time as an undergrad when he was working as an intern in a brokerage firm back in the 60s and was instructed to come up with new trading strategies that would make money. And he became incredibly frustrated because none of the strategies seemed to work. And the more he looked around, it seemed like nobody else's strategies really seemed to work over time either. You could sort of look backwards at stock prices and try and figure out something that seemed to make sense. But then as you went forward, it wouldn't work. And he just kept pressing on this idea and eventually formalized it. And what he's actually famous for is less the theory than the testing, right? So this is an interesting Nobel in the sense that these guys weren't grand theorists the way some of the economic theorists are. They're much more empiricists. These are guys who sort of took observations and then went out there. And so what Eugene Fama showed was that in essence, you can't make money easy in the stock market. There's no free lunch, right? So this is sort of the economist's way of saying that there's no free lunch, and it's an official finding of economics. And so, sort of on the flip side,
this is what they got the Nobel Prize for?
Well, so it's funny actually.
I could tell them they're not going to make any money in the stock market.
I know. Well,
I could use the money and get with the prize.
I mean, it's so economics sometimes gets lambasted for being applied common sense, but this is one of those findings that.
But no economist would ever tell you.
Well, but moreover, I mean, it's funny. This, I think, is a nice way of thinking about what a Nobel Prize is supposed to be, right? Because in essence, we look around today and we're like, of course there's no free lunch. But you go back 50 years and Eugene Fama's bosses were telling him to go out and look for a free lunch. And he was like, actually, I'm pretty sure there is none. And now he's getting the Nobel Prize for it.
Now, this is interesting. So, Jesse, you said that the economics prize was separately funded, separately created. What did that take? I mean, does anybody know?
The actual way that the prize was started was 1968 was the 300th anniversary of Sveriges Riksbank, which is one of the big Swedish banks, and they decided that for their 300th anniversary, they were going to endow a Nobel Prize in economics. And it's actually the Sveriges, I'm terribly sorry, I don't speak Swedish, the Sveriges Riksbank Prize in Economic Sciences in memory of Alfred Nobel.
You're listening to Tech Nation and Nobel Prizes Explained 2013. I'm Moira Gunn, and my guests today are professors from the University of San Francisco. They are panel chair and finance and economics professor Ludwig Chincarini, English professor Dean Rader, politics professor Stephen Zunis, astronomy and physics professor Aparna Venkatesan, economics professor Jesse Antilla Hughes, and biology adjunct professor and UCSF postdoc Jason Fernandez. Unfortunately, don't have UC Berkeley professor Teresa Head Gordon with us, but Jason Fernandez has stepped in to explain the Nobel Prize in chemistry. I know you were cribbing earlier. You were cramming in that in, so see what you can do with that.
I think it's only fair because so many biologists have stolen the chemistry prize that I actually be forced to talk about what's mostly chemistry this year, although it is applied quite a lot to biology. So the prize this year was awarded to Martin Karplus, Michael Levitt, and Ari Warshall. And the Nobel Committee cited their work in the development of multi-scale models for complex chemical systems. Once again, this is quite an earful, but I think more so than any of the awards this year, this is really a field award. These three gentlemen happen to be giants in the field. Dr. Karplus was Linus Pauling's last student, actually. We could really say this award goes to computational chemistry, or really computer modeling of chemical reactions. These guys were there at the beginning, and they really pioneered a lot of the effort there. And so if we think about the question that they were trying to answer, we know a lot of the sort of physics and a lot of the rules and sort of the mathematical rules behind chemical reactions. We can write long equations, and theorists have long said, okay, if you have an atom here and you have an atom there, they should attract each other to this amount and whatnot. But then when you have an actual molecule, like, say, a DNA molecule, you're talking, thousands, hundreds of thousands, even millions of atoms. And now you have to think, well, okay, that millionth atom is affecting that other one atom, and it becomes very complex and very hard for you to just work it out on paper, right? And so luckily, we had sort of figured this out by the time computers were starting to arise. And so people started saying, well, I can't do this, but maybe I can get a computer to do it. That's really the problem they were trying to figure out, is can we sort of simulate these sort of chemical problems within a computer? What happens is there's this sort of division in chemistry between sort of quantum mechanical chemistry. So this is when the award says it's for multi-scale modeling, you can kind of think of different scales, right? As you get smaller and smaller and smaller, I would definitely defer to my colleague in physics here, but sort of what intuitively makes sense to us starts to break down, and you have to start thinking about things on a quantum mechanical level. But on a larger level, you can sort of think in sort of classical mechanics, things that really make sense to the average person, how they sort of think about Newtonian physics. And so there's this sort of split when you're dealing with a bit of DNA, for instance. Sometimes you have to think quantum mechanically, but sometimes it's actually okay to think classically. And thinking classically is very easy for a computer to do. Thinking quantum mechanically, a computer can do it, but it's very computationally expensive. It's hard to do. And to this day, it's something very hard to do. So these three guys, and in fact the field in general, started to say, well, can we blend these two modes together and do approximations and say, I'm going to think about some things classically, and I'm going to think about the things I'm most interested in quantum mechanically, and from that I'll be able to simulate something, right? And so that has great impact when you're trying to think about, say, in structural biology, we have this sort of mantra that function comes from form. So if you remember back to Watson and Crick, they got their Nobel for studying the structure of DNA. But why is that important? It's because that structure tells us something about function. But now that you can model that structure in a computer, you can start to think about, well, that structure actually moves when it's in a cell. When it's back in that bag of water, it's moving around. So now you can actually simulate that within a computer, and you can start to think about how a drug would attach to that or do those kinds of modeling.
Well, it's really very interesting in the sense that the computer scientists are always complaining that there's no Nobel Prize in computer science, mainly because there weren't any computers around when Alfred Nobel was writing out what we'll do in my will. And at the same time,
Google should fund one.
Maybe Google should fund one. I'm liking this.
In memory of Alfred Nobel,
I'm
right?
very agnostic. Jesse, you could fund one for all I care. In economics, it doesn't matter where the money comes from. It just has to be there.
But that actually, that actually brings a great point that our colleague Teresa brought up last night, is that this would not have been possible without any of the sort of computer revolution. And one of the laureates, I forget which one exactly, sort of said, would Moore or some of the other people at Intel or some people in the semiconductor, should they share in this Nobel? Because these advances.
No computers, no nothing. Yeah. Well, I think that's true. I mean, we see that without the computers, this chemistry, the computational chemistry aspect of it, isn't moving forward. We know in modern biology, we're not doing it through the lens of a microscope anymore. We're doing it on a computer. We're doing it with information and data. Certainly there's enormous computation that we need over in the physics space for the kinds of things we're talking about. So that when we're looking at this, it's like it's an embodiment. It's like an underlayer. On the other hand, math is an underlayer to all but literature and possibly peace. There's a lot of science in the Peace Prize, though.
This year, yes.
Yeah. They certainly needed to be able to do a lot of science and engineering to detect, to dispose, to figure it all out.
It's technically very challenging.
Yeah. So, Dean, you're just over here, and you're but Matt, you could write a fiction about math, maybe.
Well, I like to think of literature as being the basis for all of this, because everyone has to write, right? None of these people would have gotten readers or acknowledged if they weren't able to write and publish. So I feel like nothing happens without the literary arts.
Good work. Would you like to have an escort from the building?
One of the things that I said last night at the talk we gave at USF was how Alice Munro is famous for her obsession on the micro details, the intimacies of human life. And one of the things I think a lot of these awards share this year is the obsession with the micro, the focus on the small thing, the keen observations of the small things that lead to the big things. Like I have argued that what makes Munro's short stories, all of which are set in this small town in Ontario, universal is their obsession and care with the particular. I think that's something that is shared among all of the prizes.
Well, let's finish up now. I'd like each of you to just give a sort of a final thought now that you've participated in this and thought about it and you work in these areas and interchange. And let me start with asking you, Jason, just for a final thought here.
Yeah, I think the thing that speaks most to me about this year's prize, both in medicine and in chemistry, is that this was really foundational work. This is very basic science work, especially if you think about the medicine prize where Dr. Sheckman's work is in yeast and studying yeast secretion. You would have a tough time getting that funded today because people would say, why do we care about yeast secretion? And then you see from another laureate's work, that work holds up in higher order organisms. You know, it explains how humans think to some extent, right? It's very important, and it's actually led to a lot of great applications. So a third of the world's insulin is now produced by yeast, secreted by yeast, directly as a result of Dr. Sheckman's work. And, you know, it's very hard to predict what the basic science will lead to. But if you just focus on applications of what we already know, you'll never get to the newer, cooler applications. So I think it was really great that the basic science was sort of rewarded this year.
Stephen Zunis.
It's hard to say what was really behind the thinking of the Nobel Peace Prize Committee, but it's rather striking that under the George W. Bush administration, there was a very active effort to undermine the Organization for the Prohibition of Chemical Weapons. And so I think this was in part an effort to underscore the importance when you have an international threat like chemical weapons that needs to be handled internationally and not unilaterally, that it be done through processes of inspection and as part of a universal agreement, not through unilateral military action.
Dean Rader.
Back in 2008, the then secretary of the Nobel Prize jury, a guy named Horace Engdahl, chided American writers. He said, quote, "The U.S. is too isolated, too insular. They don't translate enough and don't really participate in the big dialogue of literature. That ignorance is restraining." And he seemed to suggest that there would not be a U.S. writer to win the Nobel Prize for Literature anytime soon. The award this year to Alice Munro is, in my mind, a change in how the prize committee is looking at the literature prize, because many could see Munro's work as being insular, isolated, and apolitical. So my hope is that this will change things, and American writers, especially American poets, will now be considered for the Nobel Prize. I predict W.S. Merwin, the great American poet, will win within the next 3 to 5 years.
Our first prediction. This is good.
I live on the edge.
There you go. Jesse Attila Hughes.
I've seen a bunch of things around the internet and the blogosphere suggesting that this was a politically motivated economics prize, in the sense that we have one guy who's really pro-efficient markets and one guy who seems to say the markets aren't efficient. When really it's much more of a, humans are complex. And in particular, if we're going to start taking scientific principles and applying them to understanding how humans behave in aggregate, that's going to come up with the kinds of rules that you can't just sort of condense into a single soundbite. And I think if there's a general lesson for, shall we say, society on this, it's that, we oftentimes want these very, very simple, stripped-down explanations of things that affect us, economic things, medical things.
Nobel Prizes.
Nobel Prizes, right? But oftentimes, that's really not tractable. You really can't get a simpler explanation than some reasonably complex expression sometimes. And I think it's, if we want to understand these things and deal with these things, sometimes we have to hold in our head at the same time two things that seem to be contradictory and then make sense of them together at the same time.
Aparna Venkatesan.
A couple of takeaway thoughts. I think it's a wonderful stride forward for physics, for humanity. A bit of a bittersweet moment for U.S. physics, I think, with the closing of many of our particle physics facilities, like the superconducting supercollider when I started graduate school in the 90s, and recently of the Tevatron and Fermilab. Much of the momentum of discoveries has shifted abroad. Now, that's not to undermine its role for humanity and for science, but coming back to this theme of funding fundamental research, because you just don't know what wonders lie around the corner. And this is happening in a lot of area in astronomy as well, where some of the momentum is shifting abroad. I think it's something to keep in mind. Also, in my mind, I wonder about these rules of the committee, split to 3, have to be living, not posthumously awarded. I can understand the reason for that, but I wonder if it reflects the nature of the modern workforce in science. If we can give it to an organization or collaboration in peace, why not include CERN or the Large Hadron Collider? Now, yes, that's thousands of people working over a decade, but it does honor the experimental arm to science, that we need that. So I wonder about revisiting some of these rules, because basically you have to make your discoveries early on and have an awesome gene pool to live till your predictions are verified, the experiments catch up to your ideas, basically.
Ludwig Chincarini. Ludwig, you brought us all together. Thank you so much for that. Give us your final thought.
My final thought really has to do, first of all, I want to thank you for doing this, because I think this is sort of the purpose of this whole event. It's to educate and give knowledge to people. And so my final thought really is that, the way I see it, many people make decisions that are uninformed, whether it's voting in politics or even consuming a bottle of water. They really don't understand the information before they make a decision. So I think events like this, if we can continue to do this, it'll help educate people all over the world to make better informed decisions rather than sort of guessing in the dark. And that's kind of the way I'd end that.
Well, boy, that's what TechNation's all about. How about a little information before you start guessing in the dark? That's right there. Thank you all so much for joining me. Please come back. See us anytime. My guests today on Nobel Prizes Explained 2013 are all University of San Francisco professors. Ludwig Chincarini from the School of Management, English professor Dean Rader, politics professor Stephen Zunis, astronomy and physics professor Aparna Venkatesen, economics professor Jesse Antilla Hughes, and biology adjunct professor and UCSF postdoc Jason Fernandez. These professors all have blogs, and their links are available on technation.com. For TechNation, I'm Moira Gunn.